We spent 2.5 lectures on this section, so we need to try to get through this quicker. It is fun, though, don't you think? So we talked about planes and lines intersecting, and planes intersecting. Now let's talk about two lines intersecting. So if you throw two lines up in space somewhere, aside from the two lines being exactly the same, there are three other possibilities. One is that they're parallel, which means their direction vectors are parallel. Or they intersect, and if they intersect, they would intersect at exactly one point. The other possibility is that they're not parallel, but they don't intersect. Now think about that. If it was in 2 dimensions, if they're not parallel, then they have to intersect, right? But if you're in 3 dimensions, they can be parallel and still not intersect. Okay? They could be not parallel, yes, and still intersect or not intersect? Not intersect. So, if they're parallel, then their direction vectors have to be collinear or have to be parallel. If they intersect, then we should be able to find a point where they intersect, and we'll talk about how to do that. And if they're skew, well, if they're not parallel or they don't intersect, then the only other possibility is that they're skew. Okay, so the way to check for these would be in this order. We would check if they're parallel first, and then we would check if they intersect. And if they don't intersect, they're not parallel, then this is the only other option. Okay, so we can't check for something to be skew. We have to show that it's not parallel and they don't intersect. So the parallel part, I think, is easy. The intersecting part is the one that's going to take a little bit more work. And for us to do this, we want to make this into some vector form or parametric form, probably vector form, because we're interested in the direction vector. And right now, these equations, or these lines are given to us in symmetric equations. So let's transform these equations to make it look like vector form. First parallel and then vector form. So these are all equal to each other, which means we can set them equal to t. And so if this is equal to t, then x is equal to t. Y is equal to, if this is equal to t, y is going to be 2t plus 1. And then z is equal to 3t plus 2. And I wanted a different color for this. Whoops. Oops. Sorry. Man. So this is L1. So let's figure out what L2 looks like. So I want to, again, set them equal to t and then solve for the variable. So t, this is negative 3t plus 3. So x is equal to negative 3t plus t. Y is equal to negative 4t plus 7. And z is equal to positive 6t minus 5. Does that look right? Oh, yeah. If you look really, 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 really carefully. All right. that look good now? All right. So I don't know if you could see this already, but you can pull out your direction vector. They're just the coefficients of t, right? If we want to see that happen, we could transform this into, put this into x, y, and z. In vector form, and then take it apart. So all the ones with a t, or all the ones without the t, we'll put that as our initial point. And then we have t times the direction, which is the coefficients of t, which are the coefficients of t. And then that's our direction vector. That's what we want. So without doing much of the other work, I'm just going to pull out the direction vector here. D is equal to the coefficients of t, 1, 2, 3. Just to be clear, our D here is equal to, oh, maybe I should call it sub 1 and sub 2. D sub 2 is minus 3, minus 4, and positive 6. And D sub 1 is 1, 2, 3. So if they're parallel, then they're scalar multiples of each other, right? So we could do a quick check, or we can actually try to solve for 3 equations and 1 unknown. K. So D1, is this equal to K times D2 for some value of K? And then if we go through the process, we'll see that it looks like if I multiply this by -3, this might work for the first component. Or if I multiply this by -1/3, depending on how you, I guess I put K with a D. So if I multiply this by -1/3, I'm going to get positive 1. If I multiply this by -1/3, no, it's not going to work. So as it is, I don't think it's going to work anymore. So we could just say nope, nope, not parallel. So kind of like the same way we checked for 2 planes being parallel, we check their normal vectors to see if they're going in the same direction or opposite directions. Then if it didn't work, then it's not parallel, so that's good. So now the next thing to check is that if they intersect. Now if we look at the time t, if you look at t as a time variable, then we can imagine this line being drawn out in space with specific values of t. And so if they have a chance of intersecting, if they do intersect, the tricky part is that they might not intersect at the same time t. Do you know what I mean? So you're drawing this line at a specific time, and then let's say it passes through this point, and you're drawing this other line at another specific time, then it might pass through that same point, but not at the same time t. Do you understand what I'm saying? What I'm trying to say, or what I'm trying to get to, is the idea that we may need to change the parameter for one line into something else that's different from t, in case it crosses that point at a different time. Yeah, no. I got some nods, but some really confused looking faces. But that's, is there a question that somebody can ask?
That's because if t were the same, then they'd cross at the same time.
If t was the same, they would cross at the same time, then that would be nice. But there's a possibility that this blue line would go through this red point, and this green line would go through that red point, but they would go through that point at different times. Yeah, so we need, Yeah, make a new parameter. Does that make sense? Does that get there? Thanks for asking the question. So what we're going to do is we're going to take our equations in parametric form. And what we're going to do is we're going to take one of the equations, and I don't want to choose a second one, and use a different parameter. So instead of t, we'll use s. So the s kind of looks like a 5, so just understand that that's an s. Because they use s a lot because it's the next letter that comes after t. And what we're going to do is we're finding the intersection. And yesterday when I asked what do you do when you do intersections, you said set something equal to each other. So this is pretty clear what we're going to set equal to each other, right? I'm going to set the x's equal to each other, the y's equal to each other, and the z's equal to each other. What we're going to come up with here are 3 equations for the x, y, and z, and 2 unknowns. And so with the 3 equations and 2 unknowns, we're going to see if we can get a solution. So let's put those 2 together. You get t is equal to negative 3s plus 3, 2t plus 1 is equal to negative 4s plus 7, 3t plus 2 is equal to 6s minus 5. And what you want to do here is you want to take 2 equations at a time. Well, actually, you could solve this any way you want. You can solve these using matrices, or bring all the t's over to one side, the constants equal to the other side, and do some special matrix thing. For me, I think it's just as easy to solve for 2 equations at a time. I'll randomly pick the first 2 equations, and then after you get a solution for s and t, you get 2 equations and 2 unknowns, you're going to get a solution unless they're the exact same line or whatever. But when you get your solutions for s and t, you're going to plug it into the third one to see if it'll satisfy. And if it does, then you have an s and a t that would work for all 3. And if it doesn't, then it's not going to intersect. Okay? Therefore, it's going to be skew. Yes?
So if there's no solution for those group of equations right there, then it's not intersecting.
Yes, correct. It's not going to intersect. All right. So let's see. I got t already solved for here, so that seems like a substitution might be the way to go. So I'm going to put that t in there. 2t is equal to negative 4s plus 7, and t was equal to negative 3s plus 3. Oh, I'm starting to write really small. Good thing it's bigger on the screen. Negative 6s plus 6 is equal to negative 4s plus 7. Oh. All right, so 2t plus 1, that gives the distribution negative 6s plus 6. Is that a plus 6? And then plus 1, so plus 7. And then we get this. And so it looks like the 7s will disappear. And then, so s is going to be equal to 0. Okay? And then you put it back into the original equation here. So t is going to be equal to 3 times negative 3 times 0 plus 3. So t is equal to 3. All right, so we got a solution now. The way to really check that this is going to intersect is that we put the s and the t into the last equation to see if we are going to get a value, a true statement. 3t, t is equal to 3, plus 2 is equal to 6s, s is equal to 0, minus 5. So I got this is 9, 11 is equal to negative 5. So that doesn't work out. So it doesn't intersect. And because it doesn't intersect, the only other option is that it's skew. Okay. So had we got these numbers to equal and had we got those numbers to work, had we got these two sides to equal each other, then we would have said they would have intersected. And then we can either put the t in for the t for the first line or the s in for the s in the second line. And we would get the same x, y, z point. That would have been the point of intersection. All right? Does this x look like an x? Now it looks like two x's. Put on some 3D glasses. All right. Questions? Okay. All right. So that's our last of our intersecting things. We got two lines, we got two planes, and then we got a line and a plane. All right. And now let's look for some distances. Distance between a point and a plane. So let's say we had a point x1, y1, z1, and a plane with a normal vector ABC. So we can say that this plane has an equation AX plus BY plus CZ is equal to D. And so D, remember, is determined by the dot product of the normal vector and some other point on the plane. Do you remember how to find a point on the plane? No? You just put numbers x, y, z in here until it works. What? You do. So x naught, y naught, z naught is some random point on the plane. Now, how are we going to find the distance between the point on the plane? We want this distance over here, the vertical distance, the perpendicular distance between the point and the plane. And all we have is that point, normal vector, and we can randomly find a point on the plane. So I should just give you the formula and move on. But there's the thing about this is that it's kind of cool because this is where we use projection. So I think we'll go through a little bit of the process. So what we would do is we would find a vector connecting the point that's not on the plane and another point that's on the plane. And then we're going to project it on the normal. It doesn't really matter which way this is pointing. So I'm going to draw it pointing this way. And so if we do this projection, and this is a scalar projection, we would be interested in this distance right here. And that's exactly that distance over here. This distance is the distance that we would be looking for. So let's call this vector for now v, and then we have a name for this. Let's call this vector n, a normal vector. So we're projecting v onto n. But we want, let me write it differently because I just want the scalar projection. So project v onto n, and the scalar projection, I think we call it COMP, as in component projection, v onto n. And if you remember what this was, I think this was the dot product of v and n divided by whatever you're projecting onto, the magnitude of that. Hold on.
Couldn't you,
Oh, let's also take the absolute value. Couldn't you what?
because the componentizer was x1 minus x0, y1 minus y0.
Yep.
Z1 minus Z0, and so when we take the dot product, we're just multiplying the components of the normal vector onto it, and essentially it's just what you end up with is ax1 plus by1 plus
Yep.
cz1 minus g.
Yep. So if we call this P1, and we'll call this P sub 0, then V is really P1 minus P sub 0, and we're dotting that with N. And so if we remember our distribution rules for the dot product, we can distribute this with P1 dotted with N minus P naught dotted with N. And it turns out that P1 dotted with n can't really be simplified. So P1 dotted with n is just going to be A x1 plus B y1 plus C z1. P naught is on the plane, is a point that's on the plane. So if you dot any point on the plane with a normal vector, what are you going to get?
Zero.
No?
Or the plane constant.
The plane constant. So I'm going to do this off to the side here. This is really A x naught plus B y naught plus C z naught. But at some point, when we first started talking about the planes, we called that D. That's actually D. And then the magnitude of A, or magnitude of n, is just A squared plus B squared plus C squared, all under the square root. And so this is your formula for the distance between a point and a plane. Okay. So the projection was a tool for us to help us find a nice, simpler formula to remember, memorize, or at least be able to look up when you guys are doing your homework. So here's our formula, and let's do an example. So I think once you know the distance between a point and a plane, you can answer questions like what's the distance between two planes, or what's the difference between a line and a plane, provided that those two don't intersect. So here is an example of finding a distance between two planes that are parallel, so you know that they don't intersect. So they have to have a distance. And our main task is to find a point on one of the planes, and then we can use a formula to find the distance between that point and the other plane. So we'll say we have these two planes. We have plane 1, we have plane 2. If we can find a point on one of the planes and then find the distance between that point and then the other plane, then we've essentially found the distance between the two parallel planes. So let's find a point on one of the planes. Which plane should we find a point on? Doesn't matter really. The first one? The first one looks like, the second one looks like there's factors of 2 that you could take out. And if they're parallel, they should have the same or collinear normals. So if you look at their normal vectors and convince yourself they're like scalar multiples of each other. And so the first plane looks like it doesn't have the scalar multiple, so it might be easier to deal with. And as a matter of really just guessing and checking, all you really have to do is find values of x, y, z that would satisfy this plane. And if it satisfies this plane, then it must be on the plane. What would a good guess be? I was thinking 0, 0, 12, but 3, 0, 0 would work also. Remember, 0 is your friend. So 0, 0, 12 is what I thought of. Harrison said 3, 0, 0. That would also work, yeah? Because 3 times 4 is 12, 0, 0. So either one of those would work. Let's use 3, 0, 0. So the point 3, 0, 0 is on one of the planes. And so now let's just find a distance between 3, 0, 0 and this plane, 8x minus 10y plus 2z is equal to 1. And all we have to do is use that formula. So the distance, I was going to put d, but d is that other letter. So distance is equal to, the normal vector is 8, negative 10, 2, right? So let's go 8 times 3. So that's a times x1. x2 and x3 are y1 and y1 and z1 are equal to 0 and 0. So the other stuff won't matter, but I'll put it there anyways. 10 times 0 plus 2 times 0. So that's all the stuff before the d, and then you have a minus d, and d is equal to 1. D is what you get when you dot this with the plane, or dot any point on the plane. Divided by the magnitude of the normal vector, which is 8 squared plus 10 squared. It's negative, but you're going to square it, so it'll become positive. 2 squared. So 185, maybe? 64. 168 then. Yeah. On top, I got 23. What's 23. I suppose that should be good enough. This is a D distance. All right. So that would help us find our distance between any point on and the plane. Okay. So the other thing now is to find the distance between a point and a line. I don't know if that's covered in your book. Is that covered in your book? Let's do one more and see. There's one here where you have to find, oh, never mind. Point in the plane, point in the plane. Oh well. Do you guys have any? Is anybody taking a look at this homework problem from 12.5? It was assumed to have been due last Sunday, so somebody must have taken a look at it. Do you remember seeing a distance between a line and a point? No?
No, I did see it, the distance between two skewed lines.
Yeah.
Which, and despite the fact that it wasn't actually produced or sent at midnight, I spent hours on that problem alone.
All right.
And it turns out, I was just like, what? The lines are skew. At any 2 points are going to be a different length. It turns out they're talking about the closest.
Yeah, the closest distance.
The closest that they get. It doesn't specify that. It just says the distance.
Well, when you're asked to find the distance, it generally means the closest distance.
I guess I could refer that, but it was really cool.
Let's see if there's any of those. I mean, I guess if there's some in your homework, right?
It was the last one. So.
Which one? Is it here? Oh, this is in your homework, by the way.
Well, it was the last one on the set on the homework. I don't know what it is.
Oh, can't find it. You know what? One of the first example that we did was skew, right? This was skew. So let's take this problem and find the distance between those. So I'll keep it like that, and then I'll just find distance between the two skew lines. Find the distance between the two skew lines. Okay. So if they are skew, then we can imagine that these lines lie on two parallel planes. Would you buy that? So imagine, take a couple of your pens and put them askew, and then prove to yourself that they actually would be lying on two parallel planes. So put one of your pens on the ground and the other one on the table and the other one up higher, and so there's got to be a plane parallel to the table that would have those.
What configuration you put it in, you can always rotate it so that.
Right. You can always, if your skew lines are this way, you can always find two planes that are parallel so that those planes won't touch each other. Okay? So what I'm trying to say here is that if you have two skew lines, those skew lines would lie on two planes that are parallel to each other. You see? So our task is really to find those two planes and find the distance. Really what we need to do is find one of those planes. And then we need a point on the other plane. Yeah, there's only two planes that are parallel to each other. You can't find any other planes, because if you find any other planes, it'll intersect.
Try rotating one of the planes around the axis of the line, and you'll see that eventually it'll be on intersecting.
So if skew, then the lines lie on parallel planes. So what we want to do is find equation of one of the planes. And then find point on the other line. I'll put the other plane, but we're really going to get the point from the other line. And then find the distance. Between the point and plane. So, if we put these tasks together, then we've essentially found the distance, the shortest distance, the perpendicular distance between the two skew planes. All right? So it seems like the first task might be the toughest one. So we know that the normal vector is the same.
We also know that the normal vector is perpendicular to both of these lines.
So either of those normal vectors have to be perpendicular to these lines. And if they're perpendicular to these lines, therefore it must be perpendicular to their direction vectors. What can we do with those direction vectors to get a vector perpendicular to both of those vectors? No. Cross. If you take these two vectors, the vector in the direction of one line and the vector direction of the other line, you remember you can move these vectors around. So if you move them around, they can both be in one of those planes. And if you put them on one of those planes and you cross them, you're going to get a vector that's perpendicular to both of those vectors. So what we're going to do is to do this task over here, we're going to find the direction vectors for each line. We're going to cross them, and then we're going to get the normal vector, and then we'll just pick one of these lines to have the plane on. All right, let's take a look at L1. I want to put equals. L1, let's say L sub 1 of t is equal to, now we did this already, right? We solved for the x values and then we took it apart and we found the things. And what was the point for L1? Actually, I can just get it here. 0, 1, 2, and then the direction is 1, 2, 3, right? So 0, 1, 2 is a point, plus t times the direction. The direction is 1, 2, 3. L2, what's the point? 3, 7, negative 5. Negative 3, negative 4. 6. Thank you. So we have the point and the direction for each of those lines. So the normal vector for either of those planes would be the cross product of the two direction vectors. So it's 1, 2, 3. across -3, -4, 6. All right, let's see if we could do this. 12 minus -12. 12 minus -12. 24. You guys do it your own way and check my work. 6 minus -9. 6 plus 9, 15. -4 minus -6. -4, 6, 10. Can somebody verify? Double check. What? Negative in the middle. Somebody double check that? Yep. Got another okay, so we must be good. Oh. Last one's 2? Thought I was getting good at adding and subtracting. I guess not. So, 24, -15, 2. Are we good? Okay, I got a couple more nods, so I'm going with it. So remember, if this is wrong, it's your fault. Okay, we found the normal vector. Now let's figure out which plane, which line to have the plane on. So let's put the plane on L2. I just randomly selected that. Let's put the plane on L2, which means, what do you need for an equation of a plane? What do you need for an equation of a line? Point and direction. What do you need for an equation of a plane? Point and a normal. Okay? For an equation of plane, you need a point and a normal. So for this plane, we have a normal vector, and the point, depending on which line we choose, we're just going to choose L2. I randomly chose that. So this point, 3, 7, -5, is already on L2, and if we want that line to be on that plane, then we'll use that point. Okay? So our equation of a plane with L2 on it is going to be the normal vector, the coefficients of x, y, and z. So that's 24x minus 15y plus 2z is equal to, and then the d, remember, is a dot product between the point and the normal. So, ooh, these are big numbers. All right, I want you guys to figure that out and tell me. Between this vector and this point. Did we get it? Say it again. 43? I got 2 nods on that, so all right, we'll go with that. This is your plane. So if we find a point on the other plane, then we could just use a formula. Do we have a point on the other plane? This is a point that's on the line, but it's also on the other plane. And that's really all you need. So point on the other plane is 0, 1, 2. And then you just use a distance formula. Distance is equal to, I'll just say equals, how's it go again? It's 24 times 0 plus, I guess that's a minus 15 times 1 plus 2 times 2. So the 24 and 0, the negative 15 and the 1, and then the 2, and then the 2. So you're really dotting the normal vector with the point that you're looking for. And then minus d, we found d, or somebody found it, negative 43. And then you divide by the magnitude of the normal vector. It was there. You just couldn't see it. It was really, really small. Okay. All right, I'm not going to simplify that. Let's move on. So the first step looks like it should have been broken down into more steps, but it's really, that's what you have to do, is find an equation of the plane that contains both of them. You're going to do that by taking the cross product of the two direction vectors, and then use the point on one line. And then you're going to find a point on the other plane, which is really just a point on the other line. And then you're going to do some sort of projection or the distance formula. Okay? All right. So this is really a lot of fun, but I want to be done with this section already. So we're going to move on to the next section, 12.6, which is looking at surfaces. And these surfaces are called chordic surfaces.
Horticultural?
No. I should have taken my book out. I used to give a matching quiz for this when I was back at UCSC. I'd have cards, and then they would have to figure out what the equation was in the surface. So these things are just really like those conic sections, but it's in 3 dimensions. Should I just make them up? I just make them up. So these surfaces have some combinations of x's and y's and z's that are being squared. And the first really simple example of a chordic surface is your sphere, which we've seen before, right? So if you have a constant r, which will represent your radius, then your sphere equation can look like this. And of course, if your sphere is off center, then you'll just have different center points. So x minus, let's put x naught squared, y minus y naught squared, z minus z naught squared is equal to r squared. So this is also a sphere, but the center is not 0, 0, 0. Okay? Now imagine dividing out the r squared. If you divide out the r squared, you have x squared over r squared plus y squared over r squared plus z squared over r squared is equal to 1. And imagine taking that sphere and stretching it along the x or stretching it along the y or stretching it along the z. And so what you have is like a three-dimensional, what? Yeah, it's a three-dimensional version of your ellipse, which is called an ellipsoid. So can I just do this one with a center point? So it'll be x minus x naught quantity squared divided by a squared plus x minus x naught, or sorry, that should be y minus y naught. And z minus z naught squared. So if x naught, y naught, z naught are 0, 0, 0, then your ellipsoid at the origin. And then your A, your B, and your C happen to be where they would, how far they would stretch out along the x-axis, along the y-axis, and along the z-axis. Okay? All right. Now, you know how you have y is equal to x squared is a parabola? So if you had z is equal to x squared plus y squared, guess what you would have? A taco shell. It's Taco Tuesday. Yeah, this is called the first word is kind of a descriptor, an adjective really, and then the next word is the noun. So it's really called a paraboloid. But in this case, in this particular example, it's actually circular, but we generalize it to be called what's called an elliptical paraboloid. And the interesting thing about these paraboloids is that the reason it's called elliptical paraboloid is because if you make a horizontal cut along the surface, what you're going to get is an ellipse or circle. Remember, circle is just a special kind of ellipse, so if we just kind of remember that, then the elliptical kind of makes sense. But in general, this is called an elliptical paraboloid. So if I just had a z is equal to 2x squared plus 7y squared, then your cross-sectional cuts are going to be ellipses. And tomorrow we'll see how to find these cross-sectional cuts. Now the tricky part here is that if you, instead of adding them, subtract them, something weird is going to happen. Now, this is still called a paraboloid. But the descriptor now is not elliptical. What? Hyperbolic, yeah. It'll end up looking like hyperbolic paraboloid. Hyper. Yeah, so the way we're going to find these cross-sectional cuts is that we're going to let z equal a constant. So if z is equal to 1 over here, you get circles or ellipses. If z is equal to 1 for this shape, then you're going to get x squared minus y squared is equal to some constants, which is going to give us hyperbolas. Now that's going to be kind of weird. That means whatever the shape looks like, if we make our cross-sectional cuts, we're going to get hyperbolas. And what's also weird is that if we're going to make another cross-sectional cut in the bottom, we're going to get hyperbolas going the other way. So imagine trying to fill that in with an actual surface. How's that going to look like? When you make cuts down below, it's hyperbolas opening up one way, and at some point you're going to switch, so when you make the cuts up higher, you're going to get hyperbolas opening up another way. Can anybody imagine what the surface actually looks like? A saddle. What? Let's take this star out of here. See it? Everybody tilts their head to the right. No, that's not going to help.
Does it look like the DNA structure, the double helix?
No, it's not a double helix. It'd be cool to do this with a VR. I actually did it. And I took a picture of it, I think, but anyways. And so, oh, did it just change colors on you guys? So I'm going to do this. Hold on. That's not what I meant to do. So what we have here is a drawing of the surface and some cutting planes, and then on the side you would have the image of the cut that you would make. And so if I move that image of the cut, if I move the plane up and down, I see these hyperbolas, and at some point it's going to become just like an X, and then it looks like it's going to break off as hyperbolas going the other way. So these are called paraboloids because there's x squared and y squared and z is not squared. And it's called a hyperbolic paraboloid because the cross-sectional cut is a hyperbola. Yes? Graphing calculator. No, seriously, it's called graphing calculator. Look. It's something you have to buy. Pacific Tech is the company that makes it. There's this guy named Ron who, back a long time ago when they first started to do these Macs, not the old square Macs, but maybe the old, no, at some point he coupled up with with Apple and started to create these three-dimensional graphing programs that used to be free for the Mac back when you guys were really young. Do they still have that? But I don't think it's the same person though anymore. What? Oh, so yeah, so I think that's another version. Yeah, so I think that's another version. But this guy, since he got his contract revoked or whatever, he started his own company and now he does this for Macs and PCs. It's called Pacific Tech. But I was going to show you guys another program that's free, but it still uses Java. So, actually, there's a link there in the website somewhere. Anyways, this is sometimes called the Pringle. If somebody's hungry, go get a Pringle and look at it and imagine cutting it vertically with planes, and you'll see those hyperbolas come out. And you could also look at it and say, yeah, it looks like a saddle too. Right? So legs come down on one side, and then up things go up in the front and back. All right, so we got this a handful of these. We have like three more surfaces to look at, and then we want to practice memorizing them, getting to know them, so that you know the equation related to the surface and related to the names. Kind of. Yeah, but now. So, the summary.